Good morning, y'all. Um, I posted the reviews for the finals, module 1, 2, 3, and 4 yesterday. Today I'm making the video. I am going to go over what I'm going to call the good parts version, which are all the things that look the absolute most like the final. So, if you've got questions on the nitty gritty on the other parts of the reviews, you can ask me during class. But these are the parts that are the most useful for studying for the final, which is either on Wednesday, Thursday, or Friday, depending on whether you have me for second, third, fourth, fifth, or sixth period. All right, let's go. A lot of these we talked about in class, or I've talked about all of these we've talked about before in class, but a lot of these we talked about during Thursday and Friday's review. I'm going to go over them anyways, just so we have it all in one place so you can reference it whenever you want. All right, so for module 1, consider the pattern below. We've got a pattern of 3 blocks. So I'm going to go ahead and put in a 3 for my table. Here, if we count these up, there's 12 blocks. Here, if we count these up, there's 27 blocks. And depending on how you count them is how I want to think of writing block 4 or writing block n, right? A lot of people were counting them as, like figure 1 is 1, 2, 3. Here's figure 1. And you're adding, like, this situation. Or, like, here's figure 2. And you're adding this situation, right? So figure 4 might look something like this. Other people were counting them by saying, oh, it's 3. This is 3 blocks of 4 now. This is 3 blocks of 9 now. Like the middle one, the right, and the bottom. So then a block of 4 might look like 16, 16, and 16, right? If this was 1, 2, 9, just the figure squared. Other ways of thinking about this, we're finding the area in like a slightly more traditional way, which is where we do 4 by 4, but we cancel out this 2 by 2. Or we do 6 by 6, and we cancel out this 3 by 3, right? So then this would be 4 times 2 is 8, but we're canceling out a 4 by 4. However you decide to do this, hopefully we get the following for figure 4. It should look like kind of an upside down L. Here we go. And each of these should have like 4 pieces. I'm much better drawing in person and not on the computer, but that's how it goes. Cool. And then we can count those up and realize that there are 48 blocks. Great. For figure N, what I want y'all to draw on the final for figure N is just like the shape that you're finding, like the way you were counting. So if you were counting blocks of n squared, like if you were counting this as 4, 4, and 4, and 9, 9, and 9, and 16, 16, and 16, the way I would want you to draw figure N would be n squared, n squared, and n squared. If you were doing the other way I was talking about, you'd want to draw it as 2n, 2n, and an n. Right? As long as it's accurate, I'll give you the points, right? We can now either find that it's linear, quadratic, exponential, or other for this pattern, or we can find the rule and then base it off of the rule. If we based it off of the table, what I would do is to see if it's exponential, I'd see if I multiplied or divided by the same number. Here, this is multiplying by 4. Is this also multiplying by 4? No. So it must have been that this was not exponential. Okay, let's see if we're adding by the same number, right? This was plus 9. This was plus 15. Already we're not linear, right? Because linear you need to add by the same number. This is plus 21. To check for quadratic, we check the second difference. We check how the growth is growing. This was adding 6 and adding 6. This actually does mean that it is quadratic. Because when the second difference is the same, we're quadratic. To find the fifth one then, if we're doing the table method, we would increase the growth by 6 And then we'd actually do 48 plus 27 and get 75. If we instead wanted to find the explicit rule first, stupid. The explicit rule, either we can stare at this a lot and realize this is 3 times the number squared, or I can try to find the area of figure n. The area of figure n is the explicit rule. All right, this first one, the area is going to be n squared plus n squared plus n squared, which gives me 3n squared. I'm actually going to go with x because my question has it framed in x's. This second area is 2n squared, 2n times 2n, minus n squared. Let me just explain that again. It's 2n times 2n, but then we cancel out this little n by n block. And when we simplify this, this also becomes 3x squared, right? Because, where's my mouse? Here we go. 2 squared is 4, n squared is n, and then 4 of something minus 1 of something is 3 of that thing. The recursive rule is bonus on the test, but the way we do it is we say what f of 1 is. We say that the xth step is the x minus first step, so the one right before it, plus the common difference, the second difference, plus the first one. This is the format for quadratics. Again, this is a bonus. Let's run it back. New figure. I'm going to write in, this one's 4 squares, this one looks like 7, this one's 10, 13 is probably the next one. This pattern is pretty, to me, nice to see. It's just plus 3, right? We're literally saying that was the old one. We're adding 3 on the up, down, and left sides. This was the old pattern. We're adding 3 on the up, down, and left sides. So each time we're going to add by 3. If we wanted to go backwards to 0, which to be honest we're going to in a second, we would go backwards. Because we're adding the exact same number every time, it's definitely linear. Nice. And the explicit rule for a linear function is the rate of change times x plus the starting point. This is b, this is m, and this is mx plus b. For the recursive rule, I start at a point, so f of 1 is 4. And then the xth term is just the one before it plus 3. Again, bonus. For the figure, for figure 4, I just want to add 1 on each of the leaf sides for figure 3. Nice. And for figure n, where the hell is my mouse? I want to show off that each of the branches are n, and we've got this 1 in the middle, which again, if we treat our explicit rule like the area function of figure n, this makes sense to me. It's 3n's plus 1, and our equation was 3x plus 1. Right, on to module 2. Given the equation, you're going to be given an equation, and I'm going to want you to factor it and write it in vertex form. Sketch the graph after identifying some key features. These key features will come directly from these forms. So nope, my hyphen key is being pressed. Is this what I usually do? Or is it this one? It's that one. Okay. For the standard equation, this is standard form, I get my y-intercept for free. I get that the standard form tells me that the y-intercept is at 0, c, where c is that last number. It's because when I plug in 0, these two go away, and I'm just left with c. I want to find the x-intercepts, so I'm actually going to care about factored form here. This is when I multiply and get 15, I add and get 8, and whenever I've got those two numbers, here 3 and 5, I put them in my factored form. And I do not change the signs when I'm writing the equation. So here's the factored form of this equation. To find the x-intercepts, that is when I change the sign. That's when I say, given this equation, my x-intercepts where it hits the x-axis is actually at the negative versions. Great. I'm going to move this up a little bit. I'm going to care a little bit too much about how this looks. Great. For my vertex form, this is when I get the vertex and the line of symmetry, right? Oh, I've been using hearts. Let's keep it the heart theme. The vertex form, I'm always going to start this by rewriting my equation right above it, because I have like a kind of a physical way that I organize the vertex. The first step is I write in my pattern, so I'm organized. When there's no a term, which could be on the test, there's not going to be an a term. When there's no a term, I bring this down and divide it by 2. That becomes a 4. I then square the 4 to get 16. I then subtract 15 minus 16 and get negative 1. That's my vertex form, right? Written kind of by itself, it's x plus 4 squared minus 1. In my vertex, I see the number next to x and the number in the back. I flipped this number. These 3 numbers were flipped, like the sign was flipped, because they were in parentheses. And I did not flip these numbers. I did not flip the negative 1, and I did not flip the 15. Not flipped. Because they were not in parentheses. And that's how I know when to flip and when to not flip things. And then the line of symmetry is the equation x equals negative 4. You do have to write the x equals because it's a line. And it's just whatever this x was. And now we are ready to sketch the graph, right? Here we go. It's going to be the negative stuff. And then it's going to go up to 15. So I'll put it down here. Nice. In order to sketch the graph, I just find these points. So negative 1, 2, 3, 4, negative 1. These ones are at negative 5 and negative 3. Oh, shoot. Let's do it in the right colors. And the y-intercepts at 15. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then, to make it beautiful, I just draw in the U that we know parabolas look like. And if it's not perfect, that's show business. If you want to draw in the line of symmetry as well, it's the line that goes straight through the vertex. Great. The other module 2, I think this is actually a module 3 thing, but whatever. It's pretty much the same thing as graphing it, but just interpretation, right? Let me move my face. Nice. Sorry, that's a cat. It's fine. Okay, so wait, what did I make? Factored is maroon, standard's green. Factored is maroon. Standard is green. And vertex is blue. Okay, so this is like a story problem where I say I'm watching students throw their camera into the air for a new TikTok trend. This is the one where it's like in slow motion and you want to like flip your phone or whatever. And I decide that instead of stopping them, I'm going to write a bunch of quadratic equations because I'm a dork. I decide that I've actually decided that x is the time in seconds. I need to change that because I wrote x's all over the place. It's fine, but if it's t on the final, just place them with x's in your mind. It's fine. And h is the height in feet. I'm ready to go. If we want to know how high they're throwing their phones, what the tallest point of this equation, the maximum height, right? How high in total? The best equation to use here is the vertex form, because when we graph our parabola, here we kind of, silly graph or whatever. The x-intercepts are on the x-axis. The vertex is at this highest point, and the y-intercept is like our initial point. Sure. So when they're asking for highest height of anything, we want to use the vertex. We also want to recognize that time in seconds is our x, and height in feet is our h, or our y, right, our t. The thing we're plugging in is seconds, the thing we're getting out is feet. So the thing that we usually think of as x is time, and the thing that we usually think of as y is distance. So here, if we're looking for feet, we're looking for the y part. If we're looking for seconds, we're looking for the x part. Here our answer is going to be a y, and here our answer is going to be an x. Nice interpretation thing. So now, when I say, okay, well, what's the vertex? This vertex form tells me that the vertex is 0.45, 5.78, remembering that we flipped the sign here and no flip here, based on which one was and was not in parentheses. So my answer is going to be 5.78 feet, because that's the y part, and 0.45 seconds, because that's the x part. Nice. How tall is the student I'm modeling? How tall, like initial height, anytime we talk about how tall a person is in these types of problems, or the initial height in these types of problems, we're asking for the y-intercept, which comes directly from standard form and is just the c term. It's not 15. That was the last problem. It's 4. Okay. We're looking for this number. And then if we ever talk about something hitting the floor, like if we're talking about something at sea level or hitting the floor or at the ground, right? Hitting the floor or whenever the height is 0, this is asking for the x-intercepts. The x-intercepts are from factored form. There are 2 of them, and we are going to have to pick the correct one. The 2 x-intercepts we have here are negative 0.36, because we flipped the sign, and positive 1.25, because we flipped the sign. If I ask you how many seconds it takes you to do something, you better give me a positive answer, or else you're being a smart aleck. No time machines in word problems, or not in this word problem at least. So we're going to say 1.25 seconds, because we want the positive version after we've flipped the signs. This problem is a math problem, but there's no math computation. This is an interpretive problem, right? It's like reasoning mathematically rather than doing computations. So some of you might think this is way harder than computation. Some of you might think oh my God, this is so much easier. That's personal preference, but I just wanted to point that out. I think it's fun. Okay, next. Oh, your favorite stuff. Nice. Let's simplify the following radicals. We are doing this thing where we're rewriting the square root in its most basic form, most factorized form. So this is when we take the 48 and we say that it's 4 times 12. 4 is 2 times 2. 12 is 6 times 2. 6 is 3 times 2. And then we get to say all of these are prime numbers. They can't be split up anymore without using ones. So we're just going to write them like this. 48 is then going to be 2 times 2 times 2 times 2 times 3. And then j to the 8th is I'm going to draw 8 j's. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Nice. And I'm going to erase this because I'm whatever. Once we write it in our most basic form, now we get this thing where how many groups do we have of each, and how many leftovers, or what types of leftovers do we have? Because it's a square root, because there's no number right here, we're basically looking for groups of 2. Let's say, oh, here's a pair of 2s, I'll bring it out front. Here's a pair of 2s, I'll bring it out front. Here are 4 pairs of j's. I'll bring all 4 of those pairs out front. There was a 3 left over, so the 3 gets left over. Then I'll simplify a little bit. 2 times 2 is 4. 4 pairs of j's, 3 left over. If there are no leftovers, it happens. If there are no leftovers, we simply just don't write the square root. That's how it goes. Now let's try this one. Either we write out 1, 2, 3, 4, 5, 6, 7 y's and 4 x's, or we can think to ourselves, when we've got 7 things, that's 3 pairs with 1 left over. So we've got 3 pairs of y with 1 left over. And when we see 4 x's, that's 2 pairs with none left over. And we would be able to simplify like this. Part C is just rewriting things, right? If I've got an exponent that's x to the 5/8, I could have written that as the 8th root of x to the 5th. If I've got a radical that's, z to the 10th and the cube root, I could rewrite that in exponent form as z to the 10/3. Right? These are equivalent, and I want you to be able to move back and forth between them. All right. For number 2, for module 3, let's simplify the following. All exponents should be positive. When there's a power to another power, we multiply. So this is w to the 5th to the 2nd. 5 times 2 is 10. There's a multiplication right here, so I'll keep a multiplication. W to the negative 6 cubed is w to the negative 6 times 3. When we multiply these, when they're the same base but different exponents, we add the exponents. And then whenever there's a negative, we make it positive, but in the bottom of the fraction. Both of these signify division. And then with something like this, oh no, I've got to sneeze. Can she do it? No. Sad. Okay. When we're dividing things, we would say, okay, a to the 4th divided by a to the 9th is just we subtract those numbers. So 4 minus 9 is negative 5. These are all multiplications, so they'll stay multiplication. B to the 8th divided by b to the 4th is b to the 4th, because 8 minus 4 is 4. And then this is c to the negative 11, because 2 minus 13 is negative 11. We treat all the a's together, all the b's together, and all the c's together. We don't combine them. And now for our final answer, we keep all the ones with positive exponents on the top. We move all the ones with negative exponents. We move all the ones with negative exponents into the bottom, but now we make them positive because we've switched their position. Let me actually box all these answers. Nice. Let's keep going. If we want to simplify the following, now we're doing like combining like terms but with i's. It's exactly the same as if it were a variable, right? The first step we would do here is do 5 times I and 5 times 2. Get 5i plus 10. Negative 3 times 1 and negative 3 times 6i is negative 3 minus 18i. And then when we combine them, we do the 10 minus 7 and get, 10 minus 3 and get 7. We do 5i minus 18i and get negative 13i. At this point, we stop because I can't combine unlike terms. This is a number and something with i's. They're not alike. Oh my god, the cat's going nuts. They're not alike, so we can't add them. Let's run it back. The first thing we're going to do when we see square roots is simplify them. If they're irrational numbers, we have to simplify them like this, right? But if they're perfect squares, we can just say, oh, the square root of 36 is 6. The square root of 16 is 4. The square root of 81 is 9. So the square root of negative 81 is 9i. You just get to do it as if it weren't a negative and then add in your I. Multiply your I. So the square root of negative 100 is 10i. All of these were added, so I'll keep them being added. And now I get to do my 6 plus 4 is 10. My 9i plus 10i is 19i. And I don't combine these anymore because they're not like terms. Nice. And now everyone's favorite, yes. Solving the following quadratics. On the final, I'm going to give you a bunch of quadratics, and you're going to pick how you get to solve them. But you have to do one by factoring, one by vertex, and one by quadratic. You have to use all three methods, or you don't get your points. You also have to pick, right? So when I see these different quadratics, I need to say which is the easiest one to factor. I definitely do that one with factoring, right? Then which one is the easiest one by completing the square? Which one is the easiest one for quadratic formula? For factoring and completing the square, especially, my personal opinion is I want one without a's. Right? So just x squared. Right? I don't want to factor this because I'm going to have to use the box. I don't want to factor this because I'm going to have to use the box. I don't want to complete the square with these two because then I have to remember like when to divide by a and when to multiply by a or whatever. So I am going to pick one of these to be my factoring and one of these to be my completing the square. And then these two, I'm going to use the quadratic formula. That is a personal preference. If you want to do whatever you want, I don't care. But I'm going to do that like these. I'm going to do the first one using factoring. And it's because I can think of two numbers that multiply to negative 30 that add to negative 13. And I can't think of two numbers that multiply to 7 and add to 5. Right? Because if I try to do 7 and 5, I'm like, oh my god. But if I try to do negative 30 and negative 13, I am going to come up with negative 15 and positive 2. I have then, I've then factored my equation. It's still equal to 0, so I'm doing this one for number 1. Then to finish out my problems, it says totally solve the following quadratics. I want to actually figure out what my x-intercepts are. And this is when I flip the sign on both of them and box my answer. I'm feeling good. That's problem 1 done. I'm gonna move that over here. For my second one, I'll do, so I've used factoring. I don't have to use it again if I don't want to. I'm going to do my second one by completing the square. Right, this is number 2. And it's because, again, I don't really want to do ones with a terms that aren't 1 for completing the square. So I've got my thing. I write in my vertex form. I divide this number by 2. I square this number. 2.5 times 2.5. You get 6.25. I subtract this number, I get 0.75. And now I've got my vertex form. I still need to solve. To solve this, I'm going to subtract 0.75 from both sides, because I'm trying to get x alone, so I'm trying to undo everything that's happening to x. I'm going to get rid of the square by square rooting both sides. Those two cancel. This side is now just x plus 2.5. This is when I say it is the plus or minus of the square root of 0.75. So 0.75. Oh my god, y'all. Leave. Here. 0.75 square root. I can either write it as 0.75 or I can write it as 8.6. The negative means I've got an I. It doesn't change the calculation at all. It just changes the fact that there is an I out front. And then to get x alone, I subtract 2.5. Purple. I now only have x. And I've got plus or minus 0.86i minus 2.5. I didn't simplify this because I'm not allowed to. Right? The i's and the numbers can't combine, so there's no reason to break it up into a plus and a minus. This is just the answer. Great. We'll box that one over here. Then I'm going to move it as well. Ooh. The next two, so for number 3, I'll use the quadratic formula. And I will have this on the board for the final. The quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. One important thing to note is whenever there's like a bunch of numbers next to each other, these are multiplication. So we're not going to turn these into addition or turn these into subtraction or whatever. Whenever the numbers are next to each other, whenever you see this in the textbook or when you search on Wikipedia, numbers and letters next to each other means multiplication. And if you want to write that in, it could be helpful. The other part is we need to know the a, the b, and the c of our given equation. So here, our a is 2, because the thing next to x squared is 2. Our b is negative 4, important. And our c is negative 3, also important. All right, let's plug it in. Negative of negative 4 plus or minus the square root of negative 4 squared minus 4 times 2 times negative 3. All divided, that was the worst divided sign ever. Doing it again. Divided by 2 times a, which is 2. All right, and now we're just going for it. Let's simplify. Negative of negative 4 is 4. Negative 4 squared is positive 16. 4 times 2 is 8. Times 3 is 24. And a negative times a negative is a positive. That's how I'm going to simplify that. 2 times 2 is 4. Nice. 16 plus 24 is 40, pretty sure. Nice. Divided by 4. At this point, you would get most of your credit if you boxed this. Most credit. However, I do want you to simplify these radicals. So off to the side, if we want to finish it out for full credit, we would say that this is 4 times 10, this is 5 times 2, this is 2 times 2. A pair of 2's comes out front. These 2 are left over. So we would actually say 2 square roots of 10 over 4. Because square root of 40 can turn into 2 square root of 10. the pair of 2's come out as a 2. The leftover 5 and 2 multiplied become 10. And now we can divide every single thing by 2 and get our actual final answer for full credit. Nice. The last one would look similar to this. We would just plug in 2 for A, 11 for B, C for 15, and bracket. Okay. Also for Module 3. Module 3 was a huge one, remember? Also for Module 3, determine the classification of the roots of your following quadratics without fully solving them using the discriminant. Your answer should be one of the following. We should either say these are real roots or not real roots. Right? So real means no I. So no negative square roots. And not real means there's i's, aka there's negative numbers under the square root. If we're only obsessed, if we're only concerned with seeing if there's negative numbers under the square root in the quadratic equation, we really only need to check the stuff under the square root in the quadratic equation. Right? We don't need to do the entire thing. We just need to say, for this problem, b squared minus 4ac. No, more. 4ac would look like this with our specific numbers. And again, I don't really want a b here. I want a 3. For this equation, we would get negative 7 squared minus 4 times a times c. And for this one, we'd have b squared minus 4 times a times c. We want to see which one of these is going to give us a negative number, so it's not real, and which one of these is going to give us a positive number, which is real. Let's find out. Negative 3 squared is 9. 4 times 9 is 36. Times 2 is 72. There's only one negative, so it's going to be negative. This is certainly a negative number. Right? Which negative number though? 63. Sure. So this is not real. Our final answer would be not real. Great, let's check this one. 7 times 7 is 49. 4 times 6 is 12. 24. Times 3 is 72. It seems kind of right. Calculator, thank you. Absolutely not. This one? Oh, calculator's super open. Okay. What is this? 4 times 6 times 3 is 72. Nice. And then negative times a negative is a positive number. Before I even do this addition, I know it's going to be real because this is definitely going to be positive. But I'll do it anyways. 2 plus 9 is 11. This is 12. We could simplify it. It's actually really nice, but I actually don't care how nice it is. I just care that it's real. And then here we get negative 10 times negative 10 is 100. 4 times 2 is 8. Times 5 is... Sorry. Yeah, times 5 is 40. What is this? 4 times 2 is 8. Times 5 is 40. Negative times a negative is a positive. So I get 140, which is a real number. Again, I could simplify this if I wanted to. I don't. Okay, find the roots to the following equation in vertex form. This is what I'm just going to solve for x. So solve for x. Care about care about the plus or minuses. So if I want to solve for x here, I would subtract 4 on both sides. Get x plus 5 squared equals negative 4. I would square root both sides, and this is where I care about the pluses or minuses. This side, these two things just cancel, and this becomes plus or minus 2i. I said plus or minus because we did the square root. I said 2 because the square root of 4 is 2. And I said I is because we're doing the square root of a negative number. There's 3 things going on here. It looks like one step, but there's 3 things going on. And this is why math is so hard for a lot of people. Is because secretly every step is 3 steps in a trench coat. But as soon as we begin to think of this as 3 different steps, it becomes more straightforward and more manageable, right? Okay. And now we want to subtract by 5 to go move these away. We know that we can't add these together because one has an I and one doesn't. If I wanted to write these in 2 different ways, I'll say it's negative 5 plus 2i and negative 5 minus 2i. I wrote the 5 first, the negative 5 first, because of tradition. Straight up. It's mathematically correct either way, but the tradition, or the common notation, is that the real number goes first and the imaginary number goes second when we're adding complex numbers. It's just what you'll see when you look it up in a textbook or when you search it on Wikipedia. Okay, next one. I want to solve for x. I'm going to add 4 on both sides. Those cancel. I'm going to square root both sides. These things cancel. I am not going to forget plus or minus. So we square rooted, that's plus or minus. We do the square root of 4, that's 2. Do we put an I? No, because it was just a regular square root. Then we add 5 to both sides. We get x is plus or minus 2 plus 5. This is when we actually can simplify because there's no i's. So positive 2 plus 5, let me write this one in orange. Positive 2 plus 5 is 7. Write this in purple. Negative 2 plus 5 is 3. So my 2 answers here are 7 and 3. Last one of this type, not the last problem. I'm going to solve for x. I'm going to get rid of the stuff around x. I'm going to do that in reverse PEMDAS order because solving is the reverse of simplifying. It's the inverse of simplifying, right? So I moved this one over. I'm going to square root. Square root here, square root here. The 3 things I have to check for square roots are I put a plus or minus. Square root of 4 is 2. Do I have an I? Yes, I've got an I. I'm going to add 5 to both sides. I get plus or minus 2i plus 5. I say I'm finished, right? If I wanted to write them out in 2 different forms, I'd say 5 plus 2i and 5 minus 2i. Nice. And now we're on to module 4, the thing we did most recently, but it is kind of complicated, so let's check it out. I want to be able to graph the following piecewise function. Should look like this, actually, but that's just how it is in show business. Okay. Graph the following piecewise function. I've got 2 lines and I've got a quadratic. I'm going to graph the quadratic first because I think it's the hardest one. But first, I'm actually going to draw in my axes, and I'm going to do that off-centered because I noticed that my domains are between 1 and 4, so I don't actually need the negative numbers. Okay, so I'm going to write in 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 10. 1, 2, 3, 4, 5. I like to label mine by 5, so I kind of know what's going on, but it's not all junked up. Great. Let's go. I graph these. I basically think of this as its own thing. I think of this one as its own thing. and I think of this one as its own thing. I'm going to do the blue one first. This is in vertex form, which is very nice for them, for us. It means that we start vertex form for a quadratic looks like this, where if there's a negative, it means we flipped our thing. If there's an A term, it means we changed our stretch or our slope, right? If there's a number in between the squares with all the x's, that means we either moved to the right when it's negative or to the left when it's positive. And if there's a number on back, it means we moved up when it's positive and down when it's negative. So for our blue function, there's a negative on the inside. Let me do that in pink. There's a negative on the inside, which means we move to the right by 2. And there's a negative on the outside, which means we moved down by 2. So our vertex should be at negative or 2 comma negative 2. We don't have a change in slope. We don't have a change in stretch. So the quadratic is usually we go over 1, up 1, over 1, up 1, over 2, up 1, 2, 3, 4. I would go over 2, up 4 on the other side as well, except because it's a piecewise, we actually only want it between 1 and 4. So I'm only going to draw things over to positive 1 and over to positive 4. And then I'm going to stop. I have now successfully totally graphed this. If I was being super pedantic, which I probably should be, I'm a mathematician, these should be open circles because our domain did not actually include those numbers. Let's graph this line. I am going to simplify this immediately. Negative 3 plus 1 is negative 2. So I can graph down by 2 with a slope of 1 over here to draw my green line. If you don't like interpreting them, right? Totally reasonable. No, that's not what I want. I'll tell you what. No shit. Great. Let me save that right now. If I don't like interpreting like the y equals mx plus b, where's the y-intercept, which one, blah, 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 I can always plug in my endpoints, right? To find out how to graph this green line, I can make a table where I plug in my endpoint at 1 as x, find the y, so 1 minus 3 plus 1 is equal to negative 3. And then I need to plug in one other point that's in my domain. If I was in the blue line, I would plug in 1 and 4, right? But because this domain is less than 1, I'm just going to pick anything that's less than 1. I'm going to pick 0 because it's my favorite number to plug in because it's the easiest number to think about. 0 minus 3 is negative 3, plus 1 is negative 2. I graph these 2 points, negative 1, negative 3. When you plug in 1, you don't get negative 3. 1 minus 3 plus 1 is negative 1. Yeah, sure is. So, got me on that one. This is why it's important to check your work. I plot my point 1, negative 1 here. I plot my point 0, negative 2 here. And then I'll connect these points to make my line. I'm only going to connect them I'm only going to connect them to the left because all my stuff is the stuff before 1. I don't want to connect it after 1. Same thing for the red one, right? I'm going to make a table. My 2 points I'm going to plug in are 4 and anything bigger than 4. I plug in 4 for x. So 4 minus 3 is 1. So this becomes negative 2 plus 4 is 2. When I plug in 5 for x, I get negative 2 times 2 plus 4. That's negative 4 plus 4 is 0. So I get to graph 4, 2, 5, 0, and then I get to draw that line forever. Forever to the right, because I want all the stuff that's bigger than 4. To summarize, for quadratics, use vertex form to graph. And for linear lines, plug in points. Plug in points that are in your domain, either your 2 endpoints or your endpoint and then something else in the domain. Great, now we're going to kind of do the opposite, where they give us the graph and I want to write the equation. For the red one, I am going to find the slope. I went up 2 and over 2. So my slope is 2 over 2, which is 1. My y-intercept is 2. And my domain are the leftmost x and the rightmost x of my equation, which means from negative 2 to 0. Because this point is at negative 2 for x, and this point is at 0 for x. I'm going to include both of these points. For green, anytime we see a horizontal line, it's just the number it's at. Right? If you want to get really pedantic, which I love being pedantic, the slope is 0. So it's 0x plus 2, which just simplifies to 2. The leftmost x is 0. The rightmost x is 2. I've already included 0 in my red domain, so I don't want to include it in my green domain, but I haven't gotten 2 yet, so I'm going to put it in. My blue function, I went down 2 over 1, which means my slope is negative 2. And now I need to see where it hits the y-axis. I've got a couple options. I can either think about it really hard. That's what a lot of people like to do, right? To get from one point to another, I went over 1, up 2, over 1, up 2. So if I did it again, right now I'm at 2. If I went over 1 and up 2, I'd be at 4. And if I went over 1 and up 2 again, I would be at 6. So I could put in a plus 6 that I figured out by kind of just like thinking about it real hard. If I want a more systematic way, I would say we know it's going to be negative 2x plus some b. And I know that 3, 0 is a reasonable point. So I can plug in my 0 for y. I can plug in my 3 for x. And I can solve for what b would make this true. This is negative 6 plus b. I add 6 to both sides. Lo and behold, my b is 6 as well. The leftmost blue point had an x equals 2. The rightmost blue point had an x equals 4. 2 has already been included, so we're not going to include it again. 4 hasn't been included yet, so we'll include it here. Nice. And then the total domain, again, are the x's. The smallest x is negative 2. The biggest x is 4. We want to include both of those. We could have also written this like this. Let me give you the alternate ways to write this. Blue. You only have to pick one of these, so if you like one better, do it. The range, the furthest down y is negative 2. The furthest up y is positive 2. Both of these are included. or -2, both with brackets. Plus, 2 more. Let's go. Oh, 3 more, 4 more. 2 more types of problems, 2 each. Graph each function. All right, let's go. I'm going to draw in my axes first. I'm going to do it in black because it looks nice. Here we go, here we go. And then here we go. And here we go. Go. Here, we're going to use this format, this vertex format that we used earlier to interpret these 2 equations. Regardless of whether our equation is absolute value or squares or square roots or whatever, the vertex form means the same thing, right? This is a flip. This affects your stretch or your slope. The stuff inside whatever your equation is the left or the right. Right is when it's negative, left is when it's positive. And the stuff outside of your equation, whatever it is your up or down. Up or down, where down is negative and up is positive. So here, the slope is now 3 and -3. We're moving down by 4 because this number on the back is negative. And we're moving left by 2 because this number in the middle is positive. I'm graphing an absolute value function that's moved left by 2 and down 4. I'm going to move left by 2 and down 4 and put a point. That's my vertex. Now I care about the stretch and the flip. There is no flip, so I'm going to move up. The stretch is now 3, so I'm going to move over 1 and up 3 on both sides. I'm going to do it one more time so I actually have some points to connect. And then I'm going to draw my V. Let's do it again. Here, I'm moving right by 3 because the number inside is negative. I'm moving up by 7 because the number in the back is positive. And I'm stretching by 2 because my A term is 2. All right, I move right by 3. 1, 2, 3. I move up by 7. 1, 2, 3, 4, 5, 6, 7. I have messed up and made my axis too tall. So I'm actually going to... On a test, this would be me redrawing my axis. On my computer, I'm just going to move it. I'm going to copy and paste all of this and reconstruct. Wow. The power of technology. Great. I started to the right 3, up 1, 2, 3, 4, 5, 6, 7. Stretch 2 means I go over 1, up 2, over 1, up 2 on both sides, and I connect my dots. Last one, find the inverse of the following functions and then graph both the original and the inverse. I'm going to move this one over because we're going to need some space. Nice. First, let's find the inverse. The inverse of y equals 4x plus 8, the first thing we do is we switch x and y. Now we solve for y. I'm going to subtract 8 from both sides. I'm going to divide everything by 4. And then to be able to graph that, I'm actually going to say this is 1/4 x, because I divided x by 4, minus 2, because I divided 8 by 4. And got that the inverse is 1/4 x minus 2. We'll graph the original in purple. We'll graph the inverse in green. Make my axes. The original was 4x plus 8, so I'm going to go up 8. 1, 2, 3, 4, 5, 6, 7, 8. and I'm going to do a slope of 4. If I can't go to the right right 1 and up 4, I can also go to the left 1 and down 4 to find this line. There we go. For this one, I go down 2, and then my slope is 1/4, so we'll go up 1 over 4. Up 1 over, that's 3 over 4. And then I can draw that line. There we go. Flip this one over. Draw a little line to say that's another problem. Same thing, right? I'll graph my original in purple. I'll find my inverse by switching. That's a 5. My x and my y and solving for y. I add 2 to both sides. And then I multiply everything by 5. So here I added 2 and added 2. Let me write in these. Added 2 and added 2. Here I'm going to multiply by 5 and multiply by 5. When I multiply by 5 on a side that has 2 parts, I'm going to put parentheses so I remember to actually do it all. This is going to be 5x plus 10 equals y. Now it's time to graph. When I draw my axes, I realize I'm going to have to go down 2, but also up 10, because this one has a -2 as a y-intercept, and this one has 10. So I'm going to make this actually pretty low down to make sure I have room. It's actually going to be pretty hard to graph. Plus 10, 1, 2. Why do I take my glasses off to see better? Y'all, what's up? 1, 2, 3, 4, 5. 1, 2, 3, 4, 10. Starts at 10. Again, going over 1 and up 5 is actually kind of hard on this graph. So I'm going to go to the left 1 and down 5, and that still counts the slope the same. I'll then draw this line in. Great. And then for my purple one, I start at -2. I go up 1 and over 5. And then draw those points as well. So I want that to be green. No, I want that to be purple. I wanted this one to be green. Wow, the touch. All right. I don't know if that's that for that. That is pretty much what the final is going to look like. Yeah, there's no more points. If you've got questions on these, of course, we've got 2 more days to practice. And then I come before school, I come after school. This week is just going to be like math all week for me. So stop on by, ask your friends, watch these videos. There's lots of ways to get help. I'll see you soon.